For starters, if I'm thinking about the domain, the same three things that could go wrong in pre-calc are the same three things that can go wrong here. That never changes. Can't take the square root of a negative, I can't divide by 0, and I can't take the log of 0 or a negative number. I don't have any of those here. So in terms of my domain, I know that my domain is all real numbers, but because we're talking about a function of x and y, our domain is actually the set of points x and y everywhere in R2, meaning the entire xy plane will give valid heights for our y function, for our z function. So when we're talking about level curves are a way for us to take a three-dimensional object and think about what's happening in 2D, because that's easier for us to graph. So if I have a really boring shape, this is slightly conical, and a level curve would be thinking about like slicing through this at different heights. And for this particular example, no matter what height I slice through, I'm always going to see a circle. So the level curves are circles. So if I want to get kind of a rough idea of what's going on with a graph, level curves are a great way to do that. So I'm thinking about this function. And so one option is to plug in different values for z, or different values of our height. No matter what value of z I choose here, if I kind of rearrange this a little bit, I'm going to have something that looks like z minus 1 is equal to x squared plus y squared. And this has the shape of a circle. So this is a circle where my radius squared is equal to z minus 1. So if I'm thinking about that, what is, sorry, one thing there. I was trying to, it's a little, can you read that okay? Yeah. I'm like, it's just, it's not very clear. And I don't think it's the document camera. I think it's actually the projector. So, cool. If we can see well enough, that's good. Is it clear enough on Zoom, Olivia? Can you see it okay?
Yes, it works.
Okay, great.
Thank you.
We'll just go with that. So if z minus 1 has to be my radius, what's the smallest number I can plug in for z and have this actually be something? So if I plug in 2, then for sure I'm going to have a radius of 1. I could technically plug in 1, right? And 1 minus 1 was be a radius of 0. But if I tried to plug in 0, for example, it doesn't make sense, right? Radius squared can't be equal to -1. So my smallest level curve is really going to happen when z is equal to 1. So if z is equal to 1, this equation looks like 0 is equal to x squared plus y squared, which is just the point 0, 0, 1. Again, the 1 is coming from, that's my height. And if I have a circle with a radius of 0, a circle with a radius of 0 is just a point. That is also telling me something about the range of this function. So if I think about the range, we're thinking about all of the possible heights. And so the range for this function is telling me that I know that z has to be greater than or equal to 1 in order for this to even make sense. When we sketch level curves, we have two options. So I can sketch level curves on just an XY plane. So if I hold Z at 1, that gave us just the point 0, 0. If I choose another value for Z, like 5, then I would have 5 minus 1 is equal to x squared plus y squared. So 2 squared is x squared plus y squared. And I would have a circle with a radius of 2.
Can you read the points?
Yep.
That's why.
Yep. Yep, we read them alphabetically. So when I'm labeling that level curve, because I'm drawing it in 2 dimensions right now, our usual notation is actually to write this in kind of like we were talking, kind of like we were reading a topographical map. So I give the height here, and that height was at z equals 5. If I chose a height of z equals 2, then I'd have 2 minus 1 is equal to x squared plus y squared. And I would have a circle of radius 1. So that was at a height of z equals 2.
That's if it's in 3D.
So as if it were in 3D. So if I now take that same information and I actually think about putting them on a 3-dimensional curve, our standard in calculus is not the same as the standard in physics. Just sort of FYI. In physics, as long as we have a right-hand coordinate system, we might draw this in any sort of perspective. In calculus, typically, the perspective we use is that x is coming out at us. The z-axis we think of as our height. And so this is the orientation we tend to use for calculus. It's like our standard orientation for a 3-dimensional picture. So if I take these level curves and I now stack them onto this graph, at a height of 1, we just had that point. But at a height of 2, we have a circle of radius 1. And then up at a height of 5, we had a circle with a radius of 2. So as we go up, we're getting bigger and bigger circles. Now, when we talk about level curves, we don't have to take our slice at different values of z. We could also take our slices for values of x or values of y. Go back to my equation, but now I'm plugging in 0 for x. Good morning. Now I'm plugging in 0 for x. So this is the equation z equals 1 plus y squared. So for a fixed value of x, my level curves are parabolas. If I were to choose another value for x, sorry, if I were to choose another value for x, like 2, then this would look like z equals 1 plus 2 squared plus y squared, or z equals 5 plus y squared.
And the parabolas are the same. Which it just changes as it goes up.
Right, we're just shifted up and down. Yeah. So if I were to draw those level curves in like a 2-dimensional way, then my axes this time would be y and z, because I've given fixed values for x. So these would look like a parabola shifted up 1. That was at x equals 0. Parabola shifted up 5. For the x equals 2. And we can put that in on our 3-dimensional graph as well. right? Especially that x equals 0 parabola. I can kind of show right in there. I mentioned this on Tuesday, but you will not be expected to be an excellent graphical artist in 3 dimensions. We're gonna write our functions with function notation instead of writing them with a z in the mix. And if we do that, the implication, just like if I were writing in a 2-dimensional problem and I had said f of x is equal to something, we can replace the f of x with a y. So I can replace that f of x and y with a z. Thinking about domain here, again, I don't have square roots, I don't have fractions, I don't have logs. There are no problems with domain. This function is linear because all of my variables are raised to a power of 1. And none of our variables are multiplied by each other. So this thing is linear. And if we pick some level curves, all of those level curves should be lines. Should we pick some level curves by setting values of z, x, or y? Doesn't really matter. See? Sure. So in terms of sketching some level curves then.
You say that, I'm not sure that all curves are usually used.
We usually use them for z, yeah. So if I pick some values for z, this time there aren't any restrictions. I can pick positive values for z, I can pick negative values for z.
Can you put 0?
Sure, we can put 0. So let's do z equals 0, z equals -6, and z equals 3. Let's look at these 3 level curves. So if z equals 0, I've got 0 is equal to 2x minus 3y plus 12. If you had to graph that line, would you rather see that as y equals? I mean, I don't really care, but yeah, we'd probably rather see it as y equals. So if I'd rather see that as y equals, that looks like, I'll move my 3y over, divide by 3 at the end. So I get 2/3 x plus 4. If I set z equal to -6, I'll sketch them all in a second, but I was just gonna like get them all rearranged. So if I set z equal to -6, I've got -6 is equal to 2x plus 3y plus 12. Oh wait, minus 3y. I'll try not to make too many mistakes. So if I move my 3y over, throw my 6 over there, I think I'm gonna get y equals 2x plus 18 all over 3, or 2/3 x plus 6. And it's z equals 3. I've got y equals 2x plus 9 over 3, or 2/3 x plus 3. So one of the important things to note about all of those line equations, they all have the same slope, which means these level curves are a set of parallel lines. If I were graphing those level curves as a 2-dimensional picture, I can get these going in the XY plane. And at Z equals 0, I've got an intercept of 4 and a slope of 2/3. So I don't know, something like this. Up 4. And that was happening at Z equals 0. When Z equals -6, I have an intercept of, didn't really give myself enough room there. I've got an intercept of +6. They're parallel lines, and this was at Z equals -6. I've got an intercept of 3 when Z was equal to 3. One of the ways to sort of interpret these level curves or to think about what's happening with these level curves is if I imagine that I am standing, I imagine that I'm standing at a point right here, and I move in the direction of the y-axis. As I'm moving in this direction, am I going up or downhill? I know it's a really weird question to ask. But it's one way that we can interpret these level curve graphs. So if I were standing at this point and I moved in the direction of the y-axis, I'm at a height of 3 and then a height of 0 and then a height of -6. So I'm moving downhill. Yeah, so let's get a 3-dimensional view of what's happening on this graph. So there is one plane that the overall equation here is a plane, and each of these are like slices through that plane. So if I were to draw the overall plane, by the way, I know it's a plane because all of my coefficients on the variables are 1. To draw the plane, I think the easiest option for drawing the plane is to find all of the intercepts. So if I find the intercepts, so if I let x and y both be 0 in the original equation, then z should be 12. If I let x and z both be 0 in the original equation, then y should be 4. And if I let y and z both be 0 in the original equation, then x would have to be -6. I was not kind to myself in terms of drawing this, but we'll survive. So that x-intercept is sort of behind the paper. That x-intercept is at a value of -6. So it's living back there. My y-intercept was 4 and my z-intercept was 12. And if I imagine connecting those dots in a triangle, I've got this plane. And it extends forever in all the directions, right? I've just kind of shown a slice of it, but it's actually extending in all of these directions. And back to my original question, if I'm standing at a point and I move in the direction of the y-axis, I'm kind of sliding down this plane. If they weren't all parallel, right? Like here, my lines are all parallel for the slope. They're gonna have to be if it's a plane. If they weren't all parallel, then this would have some kind of twist to it, right? Because like as I move in that direction, if that line's not parallel, it's gonna kind of twist up.
So there's two.
Fit the first three on here, so. Let's do the first three real quick. So for that first one, and I tried to use all the different possible notations that we might see that are telling us to take derivatives. Again, just as a reminder. So if A and K are both positive constants, then they're kind of just coming along for the ride when I take this derivative. So I'd have 2ax minus 3k, and then the derivative of 4 would be 0. If k is some positive constant, I would choose to do a product rule here. You could multiply that all out, but I'm going product rule. So derivative of x is equal to 1. I'd leave the k minus x cubed alone, plus leave the x alone. Here we've got a little general product rule, or sorry, general power rule. So I'll bring my 3 down, k minus x squared. And then I've got to remember to multiply by -1, because that would be the derivative of the inside. And finally here, for number 3, I've got this exponential function. So when I take the derivative, that a naught is coming along for the ride. When I've got e to the something, I leave it alone. Then I need to remember to multiply by the derivative of that exponent, which in this case would be -k. Totally fine to put the -k in the front. I put the -k in the back. Questions about any of that stuff? Hopefully that feels like review, but I know. I know it doesn't always. Yes, we're getting that lovely temperature warning again. I don't really know what that means. That happened the other day too. So number 4, I've got f of x is equal to x squared y minus 3y squared plus 7x. When y equals 4, find f prime of x. So I just want to pause for a second and name that usually our brains are pretty well accustomed to think at this point in time in your math career, we're used to thinking of A and C and K as constants. It tends to mess with people if I tell you that if I name the constant Y. But I'm naming the constant Y, which means we can just plug in the 4 for Y. So if I plug in the 4 for Y, I've got f of x is equal to x squared times 4 minus 3 times 4 squared plus 7x. So 4x squared, 16 times 3, so 48 plus 7x. And when I take that derivative, I'm looking at 8x plus 7. But I could have done that the same way that you did 1, 2, and 3. In the sense that I could have just reminded myself y is just a constant. So when I go to take that derivative, the derivative of x squared y would look like 2x times y. This derivative, if y is a constant, would have been 0. And this derivative is just 7. And then I could plug in the 4 at the end if I wanted to, right? Then I can make that say f prime of x is equal to 2x times 4 plus 7. Some notation that goes along with partial derivatives. Our book uses this fun, fancy delta. This fun, fancy lowercase delta. And when we see that fun fancy delta instead of a regular d, that means we're taking a partial derivative. The other very common notation for a partial derivative is to just give a subscript of the variable that we're taking the derivative with respect to. Back to my skiing example, if I'm taking a partial derivative with respect to x, that means I'm lining my skis up with the x-axis and I'm thinking about what's my slope. The partial derivative with respect to y means I'm lining my skis up with the y-axis, thinking about what's my slope. Mechanically, to take these partial derivatives, we're doing what we were just practicing on the other page, which is we pretend that one of our variables is a constant. So when I take the partial derivative of f with respect to x, this means treat y as a constant. We don't always know what that fixed value of the constant is. So generically, we're just going to do it for any fixed constant. So when I take this derivative, I have to drag that y along with me, and I've got 2xy. When you take the derivative of negative 3y squared, remembering that y is a constant, that's going to be 0. My derivative of 7x is going to be 7. If I spin myself around and I think about lining myself up with the y-axis, this means that we treat x as a constant.
Okay, we said 2x, we just do 2x, it's fine.
It will not. So if I go back in time, just a second ago, if y is a constant, right? Like if y were equal to 4, when you take that derivative, the 4 is still there. It's trippy. It takes a little bit of practice, and then once you've got some practice, the other way to think about it, you could technically do that as a product rule. Like if that makes it settle in a little bit. If I thought about x squared y as a product rule, I would end up with 2x times y plus x squared times, and then because y is a constant, when I take that derivative, I would get 0. But the upshot is that y is coming along for the ride because it's being multiplied by the x term. So now if I flip this around and I treat x as a constant, then x squared as a whole thing is a constant, and I get x squared minus 6y plus 0. Just to make sure we're on the same page here. So when I take the partial with respect to x, that means my e to the y is a constant. So a constant times x is just going to spit out that constant. And over here, I'll have 2x y to the 5th. When I take the partial with respect to y, I'll have x e to the y, because this time my x is the constant, come along for the ride, plus 5x squared y to the 4th. Doesn't matter if you put your 5 in the front or your 5 in the middle. All the same. Good on those. Next one is a little bit gross. So I've got our f of x and y, and I'm going to go ahead and just rewrite this. So it's starting out as x squared y minus y over x. I'm going to write that as x squared y to the 1/2. Did you do this as a quotient rule? Or I would rewrite that as yx to the -1.
Yeah.
Okay, Great. So if that's what I do, then our partial with respect to x, for that first one, I'm gonna bring my 1/2 power down, x squared y to the negative 1/2, and then times the derivative of the inside, which is 2x y. Alternately, you could have rewritten that differently, because what's the square root of x squared? So you could have rewritten this as x y to the 1/2 minus y x to the negative 1. And, oh, I guess I should finish this back part. So if I take the derivative of yx to the negative 1, my negative 1 will come down and I'll have yx to the negative 2. Alternately, if this is the version you wrote, then when I take that partial with respect to x, I'd have y to the 1/2 plus yx to the negative 2. Which, if you clean this up, those will be equivalent. Which way did you all rewrite it, by the way? That one? That one. Okay. So when I take the partial of f with respect to y, I'll use this version. So I'm going to have x times 1/2 y to the negative 1/2 minus x to the negative 1. And obviously both of those you can rewrite if you wanted to. I could make that x over 2 root y. I could make that 1 over x. Lots of options for how to rewrite. On my fourth one here, got a of x and t is equal to t squared e to the xt. So when I take the partial of a with respect to x, I don't need a product rule for the partial with respect to x, because that t squared acts like a constant. I've got e to the xt, and then times the derivative of the exponent, which would be t, or t cubed e to the xt. When I take the partial of a with respect to t, now I do need to use a product rule. Derivative of t squared, I'd have 2t e to the xt plus t squared e to the xt times x. Thinking about these partial derivatives and going back to that idea of lining my skis up in one direction or the other. So I'm gonna use my head as an example. So imagine my head is now our mountaintop that we will be skiing on. So if I line my skis up with the x-axis, and the first derivative is telling me the slope, the second derivative is telling me the same thing it did in 19A. It's telling me the concavity.
What?
The second derivative from 19A was telling us the concavity, right? So if I think about the top of my head, and if I were to line my skis up in the x direction, this is concave down. What's the slope right on the top of my head? Totally. Now, if I line my skis up with the y-axis, then again, I'm concave down. What's the slope right on top of my head? And this is a local. So one of the things that we can do with these partial derivatives is the same kind of thing that we were doing in 19A, but we're going to upscale it. So I can find maxes and mins in 2 dimensions, but in 2 dimensions, to be at a max or a min, it's important that my first derivatives are both 0 and that my concavity kind of matches for both. So the example, again, I'm just using parts of my body today. So the example of what can kind of go wrong in 3 dimensions. So if I think about this point on my hand, if I were to line my skis up with the X direction right here, it's flat and I can't get really small, but imagine I could get really small. It's flat in the other direction too. But the difference this time is that I'm concave down in one direction and I'm concave up in the other direction. This is neither a max nor a min. This is a saddle point. Because it's supposed to look like a saddle, but I think it's easiest to show on my hand. I can't draw a saddle very well, but I got one with me. So to determine and to start looking at maxes and mins, it's not enough to just have our first derivatives. We also need to know what our concavity is doing, which is my motivation for why we should talk about second derivatives. So what's a little bit weird or different in 3 dimensions is we have 4 second partial derivatives. And the reason is that if I have my function of x and y, I have 2 options, right? I can take my partial of f with respect to x, or I can take my partial of f with respect to y. But after I've done that, I can take the partial of f with respect to x again. That's our notation for taking the partial with respect to x twice. Or I can first take the partial with respect to x and then take the partial with respect to y. This notation is pretty gross. I don't know whether that's the notation that our textbook uses. I'm not actually sure which notation Dr. Thomas is going to use. So I've shown both in the handout because I'm not sure which you're going to see. And my guess is on the web work, you might see both, just depending on who wrote the particular web work problem. The way that I keep this one straight in my head is I actually imagine that this gross function, like, it's some creature and the creature is eating f. So if the creature is eating f, first it hits the x, then it hits the y because it's being fed f. If I had started with the partial with respect to y, so if I start with the partial with respect to y and then I take it with respect to x, here's the creature, I'm feeding it the y, it hits y, I'm feeding it the function, it hits y first, then x, as I feed in the function x. The other partial derivative, the last of the 4, is to take the partial with respect to y twice. By the way, this one, just in terms of other ways I can write that, we can write that as the second partial of f with respect to x twice. I can also write that with a subscript with 2 x's. All of that is just notation. It's a little bit gross, it's a little bit clunky. So we'll just wait and see what notation we're using. But let's do some examples. So my first example on here, try to keep things kind of simple. So I've got f of xy is 2x squared minus 3xy plus y squared minus 4. So if we take our first partial derivatives, so the partial of f with respect to x, I'll just do partial of f with respect to x first. So if I do this one, I've got 4x
minus 3y plus 0 minus 0. So now this sort of becomes my new starting function for the second derivatives. So when I do the second partial of f with respect to x twice, then I'm starting here and saying, okay, the derivative of this with respect to x is 4. If instead I was taking my second partial of f first with respect to x, then with respect to y, I'm looking at this function and saying now if I take the partial with respect to y, I get -3. If I reset and go back to the beginning, take my partial with respect to y, it would have 0 minus 3x plus 2y minus 0. So now this is sort of my starting function. And when I look at the second partial of f, first with respect to y, then with respect to x, here I would get -3. And if I take my second partial with respect to f, first with respect to y, then with respect to y again, I would get 2.
The first, like, the derivative of x, we make it like that one first, for x minus 3y. Then after that, we differentiate again, whether it's with respect to x or with respect to y.
Right. She was gonna get a little bit messier.
Can you-
Oh. Yeah. Yeah. So 2 is gonna get a little bit messier here. I'm gonna go ahead and rewrite this as x squared plus y squared to the 1/2 power. So when I take so if I have to take the second derivatives, I start with those first derivatives. So if I take the partial of f with respect to x, I'd have 1/2 times x squared plus y squared to the -1/2 times 2x. If I'm going to take another derivative of that, I'm going to go ahead and multiply the 1/2 times the 2 and get rid of it. So that's the same as x times x squared plus y squared to the -1/2. So if I now, that's kind of my new starting function. So if I take the second partial of f, first with respect to x, and then with respect to x again, I am going to need a product rule this time. And